All right, everyone, shut the hell up. Let's begin. I'm just messing. But let's begin, all right? Welcome back to Organic Chemistry. This chapter is very easy. Like, it should not take more than 20 minutes because it's just fundamental stuff, right? Like how bonding works. That's like Gen Chem stuff. And a lot of it is going to be repeating from Gen Chem. However, as I say with everything, regardless of how knowledgeable you think you are, you shouldn't just skip over chapters. You should make sure that you thoroughly look into it and understand everything, because there's a big chance that you either didn't know something to begin with or you knew it but completely forgot, all right? Another thing is that I might mention something like, there are some very small details that I want to make sure that you know, such as, just to give you a little glimpse, right? The hybridized orbitals that your lone pairs are placed in different scenarios, as well as how exactly does pi and sigma and all that stuff work? How do those bonds get formed via our orbitals, right? So you can kind of think about what I said. If it's something that you have no clue about, then you're in the right place. If it is something that you should still be here because we want to make sure we cover everything, okay? But before we begin chapter 3, there was something in chapter 2 that I said that was a little bit misleading. I also forgot a couple of things, so I want to briefly finish off chapter 2 and then we'll jump into chapter 3, okay? Also, for anyone watching on YouTube, I very sincerely apologize for the quality of the audio in the last chapter. It sounded fine to me on the phone, but when I watched it on the laptop, it was trash. So now I'm here without any microphone. And for those of you who are here, you're in luck because you don't have to deal with shit audio because you're here in person. Unless my voice is shit audio too, but it's not, right guys? All right. So chapter 2, right, we talked about isomers, and literally the very first thing I said is that when you have two stereoisomers, and specifically like enantiomers, I said that they are the same chemically but different physically. Now the thing about me, I kind of use the terms chemically and physically interchangeably, although I know what I'm actually referring to, but it's not the best thing to do because technically it's incorrect. So I'm gonna explain to you, okay? Forget what I said about physical and chemical. It's not misinformation because I interpret it differently, but I'm gonna tell you what you actually specifically need to know with regards to the differences and similarities. And it might be like self-explanatory, but let's just go over it again because I've seen questions about this come up. So what are they identical in? They're identical in their physical properties. And what do I mean? Boiling points, right? This is one of them. What does boiling point have to deal with? It deals with polarity. These are the exact same polarity. It's just that they're going different directions. But the polarity is the same. It's the exact same types of atoms in bonding, right? So boiling point's gonna be the same. What else? We got density, melting point, mass, right? All these physical properties. No, freezing point. Okay, good question. Freezing point is the exact same thing as melting point because if you exceed this freezing or melting point, you're going to get high in energy or high in temperature, right? And that's going to melt. But if you're already a liquid and you're going below this freezing or melting point, if you go below it, you're going to become a solid. So freezing and melting are the same thing, by the way. But you guys get what I'm saying, right? These physical properties are going to be the exact same. The only physical property that's different is going to be, what is it, guys? We talked about this last time.
The optical rotation.
Yes, optical rotation, right? Now, technically, they're also the exact same in magnitude, but the direction is going to be different, right? So if this one rotates plane polarized light at negative 30 degrees, this one's going to do 30 degrees. So if you look at strictly the magnitude, 30 and 30 are the exact same. It's just that the direction actually changes which way it goes, negative versus positive. But you guys get the point, right? I said this a million times, like you guys get what I'm saying, I say that so much, but these physical things will be the same. Now, what is different other than the direction of the plane polarized light that it rotates? It's just going to be what it's able to do in chiral scenarios. So we talked about the thalidomide example last time. We talked about how one enantiomer cured morning sickness and the other one caused birth defects, right? So if you're in a scenario where you need to interact with, let's say, an enzyme, and the enzyme is only specific for the R enantiomer of your molecule, then the S enantiomer is going to try to interact with the enzyme, but it's not going to do anything. It's not going to accomplish anything. It's not going to lead to any chemical change. However, the opposing, right, the R enantiomer will do something. So in that aspect, when you're in a chiral environment, so where chirality actually matters, these will behave differently chemically. But if you're in an environment where chirality doesn't matter, like let's say you have an enzyme that just wants a 2-bromobutane, right? If it doesn't matter about R and S, then they'll behave the same. But the main difference is when you're in a chiral environment, then they will behave differently because one will fit into your enzyme or whatever the case is, the other one will not, okay? Another thing on this topic, how the hell do you separate them? What if you're doing a reaction and you get both of these? You make a racemic mixture. Remember, racemic mixture means 50% of both enantiomers. If you have a racemic mixture and I have both R2-bromobutane and S2-bromobutane in equal amounts, but I only wanted the R enantiomer or only the S enantiomer, how am I going to separate them? We haven't talked about the experimental methods or analytical techniques and separations. That comes, I think, like chapter 12 or something. But if you can kind of like think, right? If you're in OChem lab, you'll understand that polarity is a big thing, right? Polarity helps you separate things. Even if there's a slight difference in polarity, you can still separate things. But what do we talk about? These are identical in polarity, they're identical in density, so you can't even separate by density. You can't separate by anything. So how are you going to separate these? I want you to remember this because I've seen it come up before, I think in UWorld or something. But you're going to use something called a resolving agent. Okay? Just remember the word resolving. As far as the little details of what it does, it's not too important, but just to briefly explain without confusing you, a resolving agent is going to create diastereomers of both of these, okay? It's going to somehow create a diastereomer salt, and diastereomers are not the same in the sense of enantiomers, right? Enantiomers, everything is identical, but with diastereomers, the physical properties change a little bit. So because you're forming diastereomers, then you're able to selectively separate one or the other, okay? But forget everything I said, just remember the term resolving agent. This is how you separate enantiomers in a racemic mixture. Does that make sense, everyone? Need a drink of water?
Where did you get -30? Like, is that an actual value?
No, so this is just a made up value. I don't know what it is, but remember, like, if I said this is -30, then I know this has to be +30 because they're enantiomers. But this is probably not the case. It could be -70, -90, I don't know it could even be positive, right? I don't know, but I'm just saying. If they give it to you, then you know the enantiomer is gonna be opposite, okay? All right, now one more thing before we move on. So we talked about isomers and all that stuff, but there is this formula that you all should be aware of, because I don't know about people watching on YouTube, but at least here at school, they made sure you knew this, right? It's the 2 to the n formula. So 2 to the n formula is used when you're being asked, like let's say you're given a molecule like this, okay? They might ask you, how many possible stereoisomers can I get? And you're gonna use the formula 2 to the n. So n refers to number of chiral centers, okay? So in this case, we only have one chiral center. Don't forget, this is not chiral because it has 2 methyls. This is going to be chiral. So we have one chiral center. So we're gonna use 2 to the 1 to give us 2. Now, what does the answer 2 actually mean? This counts as one of our stereoisomers. And this is our second stereoisomer, right? So this one is going to be your R molecule, and this will be your S. R and S, that's 2 things total. So that's why our 2 to the n value equals 2. What if you had, let's do a molecule like this. Bromine, and let's do iodine, okay? We have 2 chiral centers. We have this one and this one. So we're gonna do 2 to the power 2, which gives you 4. What does this mean? This is one of our stereoisomers, okay? We can also do wedge dash. We can do dash wedge. And we can do dash dash, right? 1, 2, 3, 4. These are all different molecules, okay? There's no plane of symmetry. Don't think about plane of symmetry right now. You will have to very soon. But this is 1, 2, 3, 4, right? if you had 3 chiral centers, 2 to the 3 equals 8. Why? That refers to wedge, 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 dash, wedge, dash, wedge, wedge, dash, 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 wedge, wedge, all of those, right? In total, you're gonna get 8, okay? That's why we're doing the exponents, because every combination in total. So that's why you use this formula, and that's what the formula means. So, you know, if you're given a molecule that looks like this, okay? They ask how many stereoisomers. 2 to the power of n. How many chiral centers do I have? N is 0. What is 2 to the power of 0? Or anything to the power of 0 is just 1. And 1 refers to this. So, I mean, the answer would be 1, but technically there are no stereoisomers of this because this is the only thing. That is the only version of itself. And if you have the same molecule, you don't really call it a stereoisomer. The most you'd call it is a conformational isomer if it's rotated. But regardless, right, you're gonna get the value of 1, which just means this on its own. Enter plane of symmetry. Yeah, you remember this, right? So let's say we had this molecule. Okay? If I have this molecule, you're gonna try to do 2 to the 2 equals 4, okay? And let's go ahead and draw the remaining 3. Okay? So we have 4. However, as you might have anticipated, there's a plane of symmetry, at least for these 2. And it turns out that these 2 are the same, right? Remember meso compounds we talked about? And just in case you forgot, think about this, right? This pentane chain at the bottom, whether it's facing you or flipped around, that pentane is still a pentane. And if this molecule is facing you, you're still gonna have a bromine on the 2 position and the 4 position. If I rotate it, I still have a pentane and a bromine on the 2 and bromine on the 4 position. So it's gonna look the same, right? Which means that if I have this, where I'm facing 2 towards you, then that means if I just rotate it, now they're gonna be facing behind you. And the pentane, the 2 and the 4 position, all of that stuff is the same. So in other words, these 2 molecules are the exact same because they're meso. And remember what I said, meso is only going to occur if you have all wedges and all dashes. So in this case we have 2, so 2 wedges and 2 dashes. Those are the same because you can just rotate the molecule and get the same thing, okay? So what does that give us? This counts as 1 stereoisomer total, and we got 2 and 3. So our value is 3, but how can we calculate this mathematically? As I told you, for any instance where you have a plane of symmetry, you're only losing 1 of the options because 2 things will be the same, right? So we have 4 things. You're like technically not counting 1 of them because we count both of these as 1 single stereoisomer. So you're just subtracting 1, and that's exactly what you do. You're gonna do 2 to the n minus 1. That's the rule that you use. So for this one, it would be 2 to the power of 2 minus 1 equals 3. Guys, I just realized this lecture is not gonna be 20 minutes long. I don't even know how long this took already. This is, yeah. It's okay, it's okay. You can just, if you're watching on YouTube, you can speed up times 2. Or speed up times 4. That's a new option for YouTube Premium or something. But who the hell has YouTube Premium? Oh, by the way, I don't know if any of you guys have seen my videos afterwards. I don't know why you would, because you're already here. But my videos have so many damn ads. And like, I made a review video for an OChem thing, like just the class, not MCAT. And it was an unlisted video with like 2 views. And my friend was watching it, and it had like 15 ads in the span of 20 minutes. And he was complaining to me. I'm like, bro, I don't even monetize I don't even have that many subscribers. I don't know why it does that. But anyways, I apologize if there's ads on this video. All right, let me continue with what I was saying. Okay, so now I want to ask you guys something. This is a little bit of a troll question. I highly doubt you get something like this, but I want you to tell me the answer regardless. There's a juicy marker. Okay, somebody tell me what's our 2 to the n value here? How many possible stereoisomers can we get? I'll give you like 10 seconds. All right, somebody tell me the answer. What did you get for this? What did you get?
8.
Yeah, I knew this was gonna happen. Okay, what did y'all get? Did you also get 8?
I got 7.
You got 7. That's even worse. I'm just kidding. Okay. So the answer is actually going to be 4. Isn't that crazy? Once again, this is a little bit of a troll question, but I want you guys to think about these things. So what do we have? We have 3 chiral centers here. 1, 2, and 3, right? So 2 to the 3 equals 8. There's also like no plane of symmetry, so you would just end up with 8. And when you're saying 2 to the 3 equals 8, you're saying that this is going to be wedge, 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 dash, wedge, dash, wedge, wedge, dash, dash, all of those combinations. However, if you think about this thing right here, what is going on? From this same cyclohexane, these are my 2 carbons. From this same cyclohexane, I'm bonding to an oxygen. So let's look at the top one. It's bonding with a wedge to an oxygen. The bottom one, can it bond via a dash? Like, how does that work? It's coming from the same molecule. So if the top carbon's bonding via a wedge, then this one has to be a wedge. If the top carbon's bonding to an oxygen via a dash, then the back or the bottom one also has to go from the back, because geometrically it doesn't make sense. So you're gonna count this, right? There are 3 chiral centers, but when determining stereoisomers, since these 2 have to be the same as each other, or like syn to each other, you're gonna count this as one group. So you're gonna have 2 groups, okay? And they're gonna have 2 to the n equals 2 to the 2 equals 4. So 4 is going to be our answer. And once again, what that means is wedge, 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 dash, wedge, 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 dash, dash, and dash, 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 okay? Nobody ever knows this. All right. I'm a little bit paranoid. I'm pretty sure I covered everything, but give me 1 second. Let me make sure I didn't miss anything. So I don't want to go into chapter 4 telling you something I forgot. Yeah, looks like we're good. Okay. That's what's up. Okay, so now let's begin with this chapter. Let me erase everything. Okay. So really quick, I'm sorry I keep yapping. That's also gonna make this video end up being 2 hours long, crazy. But if anybody's watching this on YouTube, listen, whatever I'm telling you only applies for now, okay? This is all you need to know with regards to carbon. And I'm talking about bonding and stuff like that. I do not want to see any comments or anybody saying, oh, well, technically it doesn't work like that for nitrogen. Shut the hell up, okay? I'm telling you everything that you need to know. Of course, there's exceptions to literally everything in chemistry to begin with. But I'm telling you all you need to know and what works for carbon, because carbon is literally organic chemistry. So no comments like that, okay? And none of y'all say anything either, okay? Because I know some of y'all gonna think that I'm telling you some cap.
I got you.
All right, so to begin, carbon. What is carbon's electron configuration? Can someone tell me the electron configuration of carbon? Come on, guys.
1 is 2, 2 is 2, 2p6.
Yeah. Whoa, wait, what did you say? You said 2p what?
2p6.
No, it's not gonna be 2p6.
Shit.
Look at your periodic table. I'll give you one right now. Can I just keep this here in the video the entire time? This is your periodic table. Carbon is number 6, right? So that means it needs to have 6 electrons. So we already have 2 over here. Yeah, it should just be 2, exactly. It's okay. I think you were thinking about 6 total. Okay, I had a feeling. Unless you're lying, huh? Okay, that's great. We're gonna keep this in the background because to begin with, I wanna tell you that single bonds are going to be made up of 1 sigma bond. All right, double bonds are made up of 1 sigma and 1 pi bond. Triple bonds are 1 sigma and 2 pi. This should be easy stuff. This is from Gen Chem, I think literally chapter 2 or chapter 3, right? I wanna make sure that you guys have this down. But now we're gonna talk a little bit about why this is the case. How does this work? So in this electron configuration, let's go ahead and draw it out, right? We got 1s, and then we have our 2s, and we have our 2p. By the way, people, I think in Gen Chem, they teach you to just write 2s and 2p in the same level. It's actually not the same level, okay? I think that was, technically it should be obvious because the 2s fills before the 2p. If they were the same level, you wouldn't be filling up 2s before going to 2p. But just remember that these are not the same level. 2p is higher than 2s. That's why I'm writing it out like this. But this is what we have. We're gonna scrap 1s and we're actually gonna bring the 2s down here, okay? You know what, let me just draw 1s here, cool. So this is what we have right now, okay? let's say you have a molecule like this is a CH3. CH3 bonding to a CH3. What is this molecule called?
Methane.
Bruh. No, it's ethane. God damn it. Two methanes together is an ethane. Okay, so this is what happens, right? We all know about hybridized orbitals, right? So when you have a 2s and a 2p, what's gonna happen is to make sp3, right? We've all heard of sp3. You're going to take this orbital, right? The 2s orbital, and you're going to take all of these p orbitals, and you're going to put them in the same level now, right? So we got 4 orbitals. All of these are considered sp3. Now, take a look at this, right? This is gonna give us our first orbital. So I'm gonna write in quotes, like this is technically 2s, and these are technically the 2p orbitals, but do not refer to them as the 2s orbital or the 2p orbital. No, these are all called sp3 orbitals, and they're degenerate, which means that they're the same energy level. And what is my result going to be? Look at that. Initially, right? Initially, this third, right, the +1 orbital from the 2p had nothing. And this s had 2 electrons. But now every single one of them has 1 electron total. So the s orbital lost an electron and it shifted to the p orbital that didn't have one. And why is this? Because they're degenerate. Don't forget the Hund's rule, where you have to be the same level. Oh shit, I fucked it up. If you're in the same level, you fill one at a time before filling a second electron in the orbital. So it's gonna look like this, okay? And that's it. We're gonna leave this as that. You're not able to form any double bonds or pi bonds or anything, right? If you have sp3, the hybridized orbitals will form your sigma bonds. So how many orbitals do I have? I have 4. I have 4 orbitals. So that means that I can form a total of 4 sigma bonds, right? Total of 4 sigma bonds. And that's exactly what's occurring here. If you look at any carbon, I have 1, 2, 3, and 4. Single bonds are sigma bonds, and I have 4 of them because I have 4 hybridized orbitals with electrons in them. And that's it. That's it for this one, the sp3, you're done. Now let's move on to, guys, what is this called? Yeah, ethene, or the better term is ethylene, but ethene's the same thing. So this one right here, one second. Okay, I got scared. My mom always texts me and like, she asked me where the hell I'm at. She doesn't know I do this, by the way. Okay, so this right here, we all know as sp2, but how does this work, okay? So we're gonna take the 2s again, and now we're gonna take 2 of our p orbitals, okay? So we're going to do here 1, 2, 3. All of this will be sp2, and we're gonna have 1, 2, 3 electrons. By the way, I'm taking this one, and like the empty one, or it doesn't really matter, but keep in mind that you're gonna have 3 of those orbitals, right? I'll put an s over here, s technically, and technically p. Remember, there were 3 p orbitals, so that third orbital, you can just pretend it's here, right? And this also has its own electron. Okay, now let me tell you why I'm telling you this. If you have 3 hybridized orbitals, you can form that many number of sigma bonds. So you're gonna form 3 sigma bonds. But what does this lone p orbital do? That p orbital allows for pi bonds, okay? So take a look at this. This carbon, it bonded 1, 2, and 3, right? The bottom one is going to be your sigma bond. So 1, 2, and 3 corresponds to 1, 2, and 3. What about this pi bond? This one. The pi bond comes from the presence of the p orbital, the unhybridized orbital. Isn't that so cool, guys? Let's move on. Okay. This right here is going to be sp hybridized. Now, as you might guess, we're going to take the 2s, and I'm gonna uncircle this. Actually, I have an undo button. This one and that p orbital is going to make your, right, quote unquote s and quote unquote p. This will give you sp. You're gonna have 2 electrons. You also have this time 2 p orbitals, and these are going to have their own electrons. By the way, these are not the same energy level. Your p is gonna be higher. I'll get into that, but I just wrote it because I had no space. But what do you think is gonna happen? You can form how many sigma bonds are you gonna be able to form?
2.
Yeah, 2, right? So let's look at this. Let's look at the left carbon. The carbon on the left formed 1 sigma bond with the other carbon, and it formed a sigma bond with the hydrogen. Now we have 2 free p orbitals. That is what formed your 2 pi bonds. Okay? So that's how this stuff works. Now, if you didn't understand by now, I already mentioned in the beginning, but a single bond is just sigma. A double bond starts as a sigma, gains a pi bond, and then a triple bond is 1 sigma and 2 pi bonds. That's what it looks like. And this is exactly why it occurs. So I want you to always remember that p orbitals participate in pi bonding formation. Okay, I'm gonna repeat that. P orbitals, or something in the p orbital, participates in pi bond formation. This will be very important for when we get to the lone pairs and stuff like that. Now, when it comes to energy level, right, sp3, this has 4 things in it, right? We have 1 s, and then this shit keeps falling. Okay, we have 1 s and 3 p's. That means that there's 4 things total. Out of the 4 things, there's 1 that's s, and that means that it's just 25% s character and 75% p character. For sp2, 33% s character, and nobody laugh at this, nobody laugh. 67%, you know what, frick you guys. 66.6 and 33.3, okay? Dude, I have a little sister. She says 67 and 41 so much. I don't even care anymore if y'all laugh at it, because I would make the same joke if I was in your seat. But, right, 1/3 S and 2/3 P. All right, SP, this is obvious. It's 50-50. So 50S, 50P. Now this is important because we talked about how the P orbitals is higher in energy than the S. So where would you place sp3, sp2, and sp? sp3 would be right here, right? I know there's 3 orbitals, but forget that. sp3 is going to be up there, sp2 will be over here, and sp will be like over here, right? So you're going down. And then of course, when you're at S, you're 100% S. So you're going to be less than an sp, which is 50-50. Okay? And finally, let's talk about, not finally for this chapter, but finally for this topic. Very simple, right? I'm gonna try to keep it simple, but when you form one sigma bond, it's going to be, I'm gonna put an H over here. H equals hybridized orbital. By the way, a hybridized orbital, look it up. It looks way more complex than a circle. This is an S orbital depiction, but I'm not depicting an S orbital. I'm depicting a hybridized orbital because this is stupid, okay? So when it comes to sigma bonding, you're just overlapping 2 hybridized orbitals. So like an sp3 from one carbon to an sp3 from another carbon. That combination gives you your one sigma bond, okay? Your one single sigma bond. This like overlap. So this will be a single bond, right? Let's do single bond. Now for double bonds, you're still gonna have your hybridized orbital, but now you're going to also have a p orbital somewhere. Like, let's do this. And the p orbitals will overlap with their 2 nodes. This will give you your double bond. So remember, the hybridized orbital will always give you the sigma bond. Now with your p orbitals, right, this is one single p orbital, this is another p orbital. That double p orbital combination is going to give you 1 pi bond. So now you have a sigma and a pi bond giving you a double bond. And then if you wanted to do a triple bond, let's just draw another p orbital. Something like this, right? Now the second set of p orbitals are going to overlap, however this looks, right? If you have 2 p orbitals and your hybridized orbitals, all of those overlapping with their counterparts, that will give you the triple bond. So please remember, your p orbitals give you the pi bonds. Now there's a little misconception. People think that S equals sigma and P equals pi. P technically equals pi, but remember S does not equal sigma. I already said this like a billion times in the past minute, but your hybridized orbitals give you the sigma bond. It's not just the S. It's a combination of S and P, okay? Any questions? Okay, let's erase this. Guys, you know what I can do? Should I just do it? You know what else I can do? You know what else I can do? Wait, what's the final exam? I'm gonna give you all a final exam one day. I think I'm gonna just do this for now. Yeah. Okay? So I'm gonna show you all something. Should be very easy, but determining hybridization. Okay, let's draw some things. So when you're determining hybridization, you count, essentially number of electron domains. In total will give you your hybridization. And what do I mean by this? Let's take a look at, let me remove this. Actually, no, it's fine. Okay, let's take a look at this carbon. Okay, you know what, let me just elaborate. Number of electron domains equals single, double, triple bonds, as well as lone pair. Okay, so this carbon, this leftmost carbon, what is it bonded to? It's bonded to 1, 2, and 3 hydrogens, and it's bonded to another carbon. Okay, so over here we have 4 electron domains. In this case, they all happen to be single bonds. Then what you're going to do is write this out, SPPP. This is the most you need to do, right? There's also D, all that stuff, but all you gotta write for organic chemistry, because it's just carbons, is SPPP. Okay, however many electron domains you have, you're gonna cross out one at a time, right? So we have 4, so we're gonna cross out all of these. That means you're SP3, okay? Now, what about this carbon? That carbonyl carbon, it's bonded to 1 carbon, 2 carbon, and 1 double bond to oxygen. So in total, I have 3 electron domains. Of course, I still have 4 bonds. You have to have 4 bonds if you don't want to have a formal charge. But I only have 3 electron domains because I'm counting a double bond as 1 electron domain. If I had a triple bond, I still count that as 1, okay? So since this has 3 electron domains, when we do SPPP, SPP, that's 3 things. This is going to be SP2. Nitrogen, let's do nitrogen. Nitrogen, don't forget there's a lone pair here, right? I'll get into why. It should be obvious, but we'll get into why after. But nitrogen has 1 bond, 2 bond, 3 bond to the hydrogen, and 4 lone pair. So there's 3 bonds and 1 lone pair. That's 4 electron domains, meaning that this is SPPP, SP3. Let's do oxygen really quick. Oxygen will have how many lone pairs? 2. So I'm counting 1 lone pair, 2 lone pair, and 1 double bond. That's 3 things total, so it's going to be SP2. I don't think I should have to be explaining this, but we'll do it anyways, okay? How do we know if there's a lone pair? Just remember, this is group 15 or group 5A. That means it's gonna have 5 valence electrons if it wants to be neutral, meaning without a formal charge. And each bond, right? Each bond, what is a bond? A bond is literally 2 electrons. I'll put X over here. A bond is literally 2 electrons. So if I'm bonded to 3 things, we're saying that 3 electrons came from the nitrogen. Of course, it's gonna have a full octet with the bonds, but how many came from the nitrogen through covalent bonding, right? It's gonna be half of the number of bonds, or half of the electrons participating in the bond. So there's 3 electrons coming from the nitrogen, in this case, right? So you know that you have to have 1 lone pair, because I'll give you 1, 2, 3, 4, 5, which matches up how nitrogen, group 15, group 5A, has 5 valence electrons. Same thing for oxygen. Oxygen has 2 bonds, right? 2 bonds equals 4 electrons total, but half of that came from oxygen. That's 2. Then 3, 4, 5, 6. Group 6A, group 16 has 6 valence electrons. That matches up, okay? You guys knew this, right? I know you're trolling, but you knew this. And if you didn't, you're cooked. All right, let's do a few more examples. Because there is an exception, guys. There is an exception. There always is an exception, kind of. Let's say we had this, this carbon is sp3. This carbon, 1 bond, 2 bond, and 2 hydrogens, sp3. What about this carbon? This carbon has 1 bond over here and 1 triple bond that way. That's 2 things, so that means that this is sp. Nitrogen, right? This is gonna have a lone pair. So this has 1 triple bond and 1 lone pair. That's 2 electron domains, meaning that this is also sp, which is sp. Okay. Cool. Now, what happens if you have something? I don't have a black marker. Do you guys have a black marker? No. It's okay. Blue is our new black for today. This is the most common example they ever give. Okay, guys. Nitrogen, what does the electron hybrid orbital thing look like? 1 bond, 2 bond, 3 bond, and lone pair. So it looks like sp3. What is the problem with this, guys? What is the problem with this? You should all know this. This should not be this should not be brand new to anybody. This should be review. What is the problem with this? Somebody tell me. Exactly, right? What can this molecule do? This molecule, this nitrogen, is able to resonate with this oxygen. And as a result, you're going to get this. This is an ugly resonance structure, but it is a resonance structure. It's still able to occur in small amounts. What is the hybridization of this nitrogen now? 1 bond, 2 bond, 3 bond. That's 3 things, that's sp2. And because it has a plus charge, there's no lone pair. Otherwise, that would be way too many electrons. So now this looks like sp2. What the hell? sp2 and sp3. What do we do here? You always take the lower one. If you have sp3 and sp2, you're gonna be sp2, okay? Because what is resonance about? Resonance is a hybrid structure. So you're never gonna be fully this, and you're never gonna be fully this. You're gonna be like a hybrid of them. You might look more like one than the other, but this lone pair is not fully there, okay? I'm gonna get into that. This lone pair is not fully there because it's participating in this resonance. So you're not gonna ever be fully sp3, therefore you say you're sp2. So this nitrogen is sp2. Okay, now let's talk about what hybridized orbital are these lone pairs in. We talked about what hybridized orbital these nitrogens, oxygen, and carbons are in, but what about lone pairs? Let me go ahead and redraw real quick. Okay, guys. So, of course, nitrogen is sp2 and oxygen is sp2 as well. Really quick. I think I just said really quick twice. But look at this oxygen. Right now it looks like sp3, right? Because we got 1, 2, 3, 4. Remember, because it can become sp2, you call it sp2. So both oxygen, even this carbon and nitrogen, those are all going to be sp2. But what about these lone pairs? Somebody tell me very confidently what fucking hell, bro, I can't speak. Dude, I swear to God, English is, you know what? English is not my first language. I'm gonna use that as my excuse. Urdu was my first language. I used to speak it fluently, but then I still speak it relatively fluently, but my parents, they were like very concerned because my brother, who's like a year and a half older than me, when he started school, he didn't understand shit because English, he didn't know anything about it, just straight up Urdu. And I was just like him, right? I didn't understand shit. So then my parents, they were like, you know what? We're gonna be very different from regular Desi families. We're gonna speak in English only in the household. And slowly the fluency in Urdu went away, but English became number one. However, I still technically claim Urdu as my first language and English as my second. However, you would never know based on how, actually you would, dude, I speak like an idiot sometimes. Like I just stumble my words. But like, okay, I'm sorry for going on a tangent, but like here's the thing. If anybody like speaks several languages, or if you're learning a new language, you realize that like you mix languages even if you're not trying to. Like I speak Urdu, Hindi, and also Spanish. And whenever I'm speaking Urdu, I'll say a word in Spanish or vice versa. And then when I'm speaking English, my whole like verb, noun, directionality shit just messes up. And so I also tend to forget my words because I'm thinking of a different language. But this was a shitty yap excuse for my bad vocabulary. Dude, I can't even say vocabulary properly. Anyways, forget that. That was a whole side tangent. All right, let's continue back to this. So, I might cut that out the video. That was stupid. Anyways, this molecule right here. Somebody tell me very confidently what hybridized or unhybridized orbital is this lone pair in for the nitrogen. Somebody tell me very, very confidently.
sp2.
Hell yeah, bro. Hell yeah. Just kidding. You're fucking wrong, bro. So we got the answer sp2. Guys, what did I tell you in the very beginning? Let's see if it's still there. I don't remember what I erased. Okay, actually right here. What did I say over here? Your sp2 hybridized orbitals will participate in sigma bond formation. So meaning you can have a carbon. One of these bonds in the double bond will come from one of the orbitals, and then the other two, right? The other two will also come from the hybridized orbitals. Where does this pi bond come from? This pi bond. This comes from the p orbital, right? Now you're remembering, okay? So that means, since this lone pair is participating in pi bond formation, right? This is a pi bond that it formed, because we already had a sigma. You have to have a sigma if you want to add a pi bond. So because this is participating in pi bond formation, that means that this is in the p orbital, okay? This is in the p orbital. What about this oxygen? What are the lone pairs going to be in?
One in P with sp2.
No, they're both going to be sp2. Why? Let's take a look. If you did resonance, you brought this down and you kicked that up. You kicked it up. These two lone pairs are already there, right? They're already there. But now, this pi bond broke off into electrons. So these two blue lone pairs were already there. And if you go back to this, just the purple electron is participating in that pi bond formation. So this purple one you can say is p orbital, but the two blue ones, those are always there. That means that these are also going to be hybridized. These are both going to be sp2. Okay? So if you're participating in pi bond formation, you have to be p orbital. If you're not ever participating, you're going to be hybridized. Does that make sense to everyone? Okay.
Why did they give you three of them and they all look the same? How do you know which one is which?
Yeah, so that's a good question. So if you have several electrons, generally the ones that are hybridized will just stay hybridized. Those will never participate. As far as determining which one is hybridized, which one is not, they're not going to do that to you because it could be either or, right? It could be a 50-50 or whatever, 30% chance. So all you got to know is that in a case like this one right here, two of them are going to be sp2 and one will be p. So like they could ask you, what are the orbitals that these lone pairs are in? And an answer choice for this case, the correct one would be sp2, and p respectively, or something like that, okay? That's how this is going to work. All right? All right, guys. Why does this keep dropping? So, now let's talk about bond angles, and we're going to relate it to our hybridization. Guys, I'm gonna be a rebel and erase this. Dude, I hope this wasn't like supposed to be here. I hope it was just something old. I'm gonna just leave everything on the board. Should I do that? That's gonna be so evil. So, SP2, no, SP3, SP2, and SP. Very simple, right? When it came to Gen Chem, there's a lot of geometries to remember, but for OChem, it's very simple. Just 3 geometries to remember. SP3, tetrahedral. SP2, trigonal planar. SP is linear. Okay? What's next? Tetrahedral is going to have 109.5 degree angles. Trigonal planar will be 120 degrees, and linear 180 degrees. Definitely know this, right? Don't shy away from knowing geometry, just know it, okay? It's very light for organic chemistry, but just know this. So, if you have a molecule like this, right? And I'm asking, let's call this carbon 2, carbon 1, and carbon 3. They might ask you, what is the bond angle between carbon 1, carbon 2, carbon 3? The thing in the middle is your central atom. So essentially, I'm asking, what is this bond angle? Because I know that this is sp3, it's tetrahedral, it's going to have a 109.5 degree bond angle. Okay? What if I had this? And I'm asking about this carbon, the bond angle over here. This is 1, 2, 3. That's sp2. sp2 is trigonal planar, so that means this will be 120 degrees. Now, of course, you guys might remember from Gen Chem that when you have a double bond present, the double bond kind of like pushes away your single bonds, and so that bond angle actually becomes less than what it is. So technically, this is negative or less than 120. I don't think it's that important. Maybe just keep it in the, in your mind, in the background. But just keep in mind that the ideal angle here would be 120 degrees. And then finally, if we have this right here, and you're asking the angle like this is linear. As you can tell by how it's drawn, this will be 180 degrees. And this one cannot deviate, because if you're saying a triple bond is going to push the single bond away, it's going to push it this way and that way equal amounts. So it ends up just being fully linear. So this is going to be 180 degrees. So when we go back to this example, what is my actual bond angle between like this carbon, the nitrogen, and that carbon, or even this hydrogen? Is going to be 120 degrees, because this is not sp3, it's sp2. Okay? I'm gonna bring back some nightmares for you guys. I don't think they're gonna ask this on your MCAT, but if you're being asked the nitrogen lone pair, nitrogen and like carbon, so the angle between this lone pair, nitrogen and a carbon, do you guys remember what the angle is gonna be? Yeah, exactly. This is one of those weird ones that you're just going to like always remember. It's just like, it has to do with like the orbital, the shape and the orientation of it, but this one would be 90 degrees. I've never seen this show up. It's just something they throw at you in class, but it's good that you guys remember this. At least you remembered it. Okay. Yeah. Any questions, guys? Dang it. Okay. Oh, you know what I'm gonna do? I'm gonna leave this up here. So we can have a board full of chemistry. Looks like I wrote up there, right? We are almost done, guys. Let's make sure I didn't miss anything. We're gonna talk about some fun stuff now. We already started talking about it, but resonance. Resonance and how it works, okay? This will be like technically the last thing that we're gonna talk about. And then we'll be done for this chapter. Anyways, let's talk about resonance. So resonance is simply the delocalization of electrons. And delocalizing electrons is good, because if you have just an electron a lone pair there, or like a negative charge, versus if you're able to just move it around, right? Move it there. These are fake structures, by the way, but I'm just saying if you're able to move it around and stuff like that, that's going to be very good. So that's good, because if you're localizing a charge in one place, first of all, charges, it's never like, you shouldn't have charges. That's like stupid, right? To say the least, like you'd rather be neutral than hold a charge. But if you have to hold a charge, you want to spread it around so that's not concentrated in one area. It's better to have it just dispersed. So that's what resonance is all about. Resonance is always, well, for the most part, it's going to be good. When you guys get into aromatics, you're going to learn about something called anti-aromatic. I know, right? And that's going to have resonance, but it's not even going to be true resonance. It's going to be fucked up for real. But don't worry about that. I need to stop digressing. Anyways, delocalization of charges, right? It doesn't have to be electrons per se. You can just say delocalization of charges, which ends up making molecules more stable. Okay? Now you can delocalize anything, negative charges, positive charges, and radicals. We're not going to talk about radicals because radicals don't ever show up for your MCAT in terms of resonance. But I want you to keep in mind that radicals will follow the same exact order as cations in terms of how the resonance works. So let's say you have this right here, okay? Resonance will occur if you have a charge that's one away from a double bond, or in some cases a lone pair, okay? So we have a charge, it's one away from a double bond. So when you have a negative charge, you're going to move negative towards the double bond. So this is going to come down here. And what happens at this step? Too many bonds, right? So something has to move. You can't just break a single bond, but what you can break is a pi bond. A pi bond you can break off and make into electrons. So you're going to end up with this structure right here. Okay? And you can also go backwards. You can bring this down and kick that up as electrons. Now, when it comes to resonance structures, these are hybrid. So you might see sometimes like this. This means that the double bond is constantly moving around, and it's moving around so much that they just put dashed lines. They don't even draw a definitive double bond anywhere. And both of these are going to have the partial negative charge rather than one of them having a full negative charge. But this is composed of both of these, okay? Now, when it comes to these hybrids, these hybrid structures, it doesn't necessarily mean you're equally this and equally that. In some cases, it can be that. Let me draw you a quick example. If I had this, right? The resonance structure of that looks like that. These are literally identical because in this case, you have a double bond O and a negative oxygen. In this case, you have a double bond O and a negative oxygen. So these will be literally 50-50 in terms of their resonance. But in a case like this, where you have a negative on a carbon versus negative on an oxygen, it's not the same because they're not the same structures. One of them is going to be better than the other. This is where major contributors come in, right? So we'll talk about major contributors more, but in this specific example, it's better for the more electronegative atom to hold that negative charge. So this is the major contributor out of the two resonance structures. You will still get this resonance structure, but your hybrid resonance structure will be more like this structure right here. Does that make sense? Okay. So that was one example. Okay, so that's just like general like negative, right? Like here, let me just give you another one. Right, if you wanted to delocalize this, you bring this down towards the double bond, and the double bond has to kick off to the next carbon, and so you'd end up with that, right? Okay, so you can delocalize the negative charges. You can also delocalize just straight up electrons, okay? Keep in mind, a negative charge is just in another lone pair. It's an electron. So for that reason, we already did this. But you can have resonance over here. How is the resonance going to look? Form a double bond here, and kick this up like that and onto this carbon. What does this give you? I need to start using different colors for this. But look at this. We had nothing to begin with in terms of charges, and now we have positive and negative. This is still a resonance structure. It's going to occur, and these will be like hybrids. It will be a hybrid structure. Which one looks better though? The top or the bottom one? Of course, the top one, right? If you are being asked the major contributor of this, you choose the one with less charges, because if I have no charges, I'm neutral. That's better than having charges over here. Of course, positive and negative cancel out. But like, why do you want to have charges if you don't need to have charges? Doesn't make sense, right? So keep in mind, this is a very ugly structure, but it still is possible. It still is a resonance structure. This nitrogen is not sp3, it's still sp2, but your resonance hybrid will look more like the better one, okay? Now let's do one more. This time we're gonna do positive charges. Okay, when it comes to positive charges, instead of having two motions, like you see over here, we had two arrows. Over here, we had two arrows. Positive charges will have one single arrow. This time you're moving towards the positive charge. You're moving towards the charge. Over here, we had the charge moving towards the double bond, and over here we had lone pair moving towards the double bond. But this has no lone pairs to move, right? You're positive, you're lacking electrons. So instead, you're going to move the electrons towards it. So you're gonna have one single motion, okay? You're gonna move it towards there, and what do you end up with? First of all, your double bond is here. Where does your positive charge go? Just think about this. This carbon had 3 bonds, right? Carbon, carbon, hydrogen. This carbon had carbon, double bond, and a hydrogen. And this carbon had carbon, carbon, double bond. Okay? When you form this double bond, this carbon right here, it's neutral because look, you still have 1 hydrogen, you still have this carbon, now you have 2 bonds. That's 4 total bonds, full octet, chilling. This carbon is still bonded to a hydrogen, it's still bonded, what the hell? Okay, it's still double bonded and has a bond over there. That's 4. What about this carbon? This carbon was carbon, carbon, double bond. This is carbon, carbon, single bond. This carbon is lacking a bond now. So the positive charge is over here. I'm gonna erase this. But this is how you resonate positive charges. You're going to move it towards, the double bond towards the positive charge. And we didn't talk about this yet, but this is OChem 1, so it should be obvious. But the better structure is going to be the tertiary one because you want more substituents when it comes to positive charges because of the electron donating effects of the alkyl groups. So this is the major contributor. Okay. And okay, you know what? I'm just gonna tell you anyways. I hate bringing stuff up and then like telling you I can't tell you, now I have to tell you. Let's just do radical really quickly. Okay? If you had a radical to resonate, the short answer is to just do this, right? The short answer is that. But the actual way you do it, this is 1 single electron. So you're gonna use 1 electron here, half arrow, and 1 electron from here, half arrow. This is gonna form your double bond. But there's still an electron here. This electron will go to that tertiary carbon, so you end up with that. If that made no sense, forget it, okay? Just treat it as a regular cation, but that's how it works. Okay, now let's talk about... Okay, don't worry about it. Just watch the video, bro. I'll show you after, Okay, let's talk about how do you determine major contributors. So we talked a little bit about major contributors, like what that is. Major contributor is just the best of your structures. So determining MC, major contributor. Okay, step 1, no charges. If you have a bunch of options and one of them has no charges, the rest of them have charges, the one with no charges is better, right? We'll do this example again. This is one resonance structure, if you want to call it that. And this is another. resonance structure. Between these two, the left one has no charges. The right one has 2 charges. The one with no charges is better. So simple, this one is our major contributor. However, let's say that the number of charges is the exact same. Next, you want to look for full octets. Okay, so what is an example of looking for full octet? Let's do that. This is one, shit, I always forget something. Okay, this is one structure. We have a lone pair on the nitrogen. We can form a double bond here. And what is our resulting molecule? It's going to be this, okay? The red molecule, the carbon, okay, if you ever have a carbon with a positive charge, it will never have a full octet. That's just easy, something you should be able to recognize by now. But everything else like nitrogen and oxygen, those will be full octets even if they have a positive charge. So this one, it has, right, just a hydrogen there. That's 1, 2, 3, 4, 5, 6. In terms of electrons, that's 6 electrons. That's not a full octet. So this one does not have a full octet. This one, on the other hand, nitrogen. There's 1, 2, 3, 4 total bonds, including single and double bonds. 4 times 2 is 8. That's an octet. So between these two, they both have one single charge. They both are positive charges. The difference is on what atom that positive charge is on. In this case, the nitrogen has a full octet. Over here, the carbon does not have a full octet. So you're going to prioritize full octets, making this one the major contributor. Okay? And finally, let's say that everything has a full octet, or maybe you're comparing like 3 molecules and 2 of them have full octets and 2 of them have charges on them. Then what do you do? Put like least charges. Then you look at if electronegative atom, the most electronegative atom having the negative charge, and the least electronegative atom or the electropositive atom having a positive charge, that will be better. So what do I mean by this? Let me see. I'm gonna make up a fake molecule. Okay, just pretend this exists. Versus. Guys, this is not real. Okay, nobody kill me, please. So between these two, pretend they're real resonance structures. Which one is better? So they both have the same amount of charges. Okay, we're getting past this. Number 2. They both are going to have everything with a full octet, including the oxygen. Wait, pretend fuck man. Here, okay, there we go. And this one, just pretend it exists. So they're both gonna have full octets. Just remember, oxygen and nitrogen with the positive charge will be full octet. So whatever, just forget, okay? So they both have the same amount of charges, they're both positive charges, and both have everything with a full octet. So what is that last thing you look at? You look at what type of atom do I have with the charge? Oxygen is more electronegative than nitrogen, because this is the direction for electronegativity. So since oxygen is more electronegative, nitrogen is more electropositive. The electropositive thing would rather hold the positive charge. So between these two, this is the major contributor. If we were looking at negative charges, and a negative, right, then the one that's more electronegative would like the negative charge better because it likes to hold negative charges and more electrons. So that would be this one, okay? So that's what you want to look at. And of course, nitrogen is very electronegative. It's, I think it's like the 4th most electronegative atom or something like that. But oxygen is oxygen is actually the 3rd most. I just heard something the other day that was like, that contradicted everything I've ever heard. But forget it, right? Oxygen is more electronegative than nitrogen, even though nitrogen is already very electronegative. So the one that's more electronegative will still take priority in terms of getting the negative charge. Okay. So please remember what I just talked about, because I'm gonna give you a question at the very end. I just want to talk about one more small thing. Conjugation. So conjugation just means alternating single and double bonds. So if I give you this molecule right here, I have 3 double bonds in conjugation because I have double bond, single bond, double bond, single bond, double bond. And the good thing about these is you can just resonate like crazy, right? This is why benzenes are amazing. Benzenes are aromatic, by the way, so that's its own separate thing. But you're able to just go around, right? And make the exact same molecule, but you're shifting around the double bonds. And that's very good. That's something that plays a role into aromaticity, which we're not going to get into at all. But conjugation, just keep in mind, it's good. If I had a molecule that looks like this, these are not conjugated because, look, this is too far from that double bond. So those are not conjugated. Okay, that's all we need to know for this. Now, to leave you all with a very fun question. I'm not gonna lie, I think it's actually very easy, but I'm gonna give it to you anyways. I purposely brought up conjugation and switch topics because I want to see if you're gonna remember how to answer this question. Give me a second though. I don't remember any of my practice questions. All right, guys. So these 4 molecules right here determine the major contributor. I'll give you literally like 10 seconds. So I'll give you 10 seconds. I'm gonna put like letters A, B, C, and D. What is the major contributors? Or are there multiple? Because you can have multiple major contributors. So take a look and let me know. Just yell out the answer when you have it.
A.
Okay, we got 1 answer for A. Anybody got B as an answer? What do we know it's definitely not going to be?
Not C and D.
Right, C and D, obviously not because neither of these have a full octet. It's between A and B. What is the confident answer, guys?
Choice B.
Good job, right? It's going to be choice B. Because nitrogen is less electronegative than oxygen. So nitrogen would rather hold the positive charge, making this our answer. All right, any questions, guys?
Are those double bonds considered conjugated like that?
Yeah, for this one, yeah, these, I mean, both A and B, even the rest of them, you can consider them as conjugated. For example, like this one, right? When we say conjugated, remember the thing I told you? Like you can just straight up move double bonds around like constantly. So if you look at this, I can move this over here and move that electron up there. What is this going to give me? It's going to give me this structure right here because I formed a double bond and I got rid of the charge. Just have an H, by the way. Alternatively, I can do this, right? That and that. That's going to be the same thing as this. And so, you know what I'm saying? Like you can go from here to here or here to here through the double bond movements. You can also, damn it, I forgot the H. But that's how you want to think about it. That's very good that you brought that up for sure. Okay, anybody else have any questions before we finish off? Bro, I wanted to do chapter 4 today, but I can't anymore because chapter 4 will be extra long because we're covering SN1, SN2, everyone's favorite. Oh, I'm gonna love it a lot. I'm really gonna love it. But my mom was asking me where the hell I'm at, and I have to bring home some food, so I have to dip. But if you have any questions on YouTube, please leave as many comments as you want, and of course I will get to them. And guys, if you're watching on YouTube, please check the description. I always put a link to my WhatsApp group chat as well as, it's like a link tree thing. So it has my group chat, has my socials where I post daily practice questions, daily. And I also have resources and I'm planning to add a bunch of more things. So definitely read the description, drop a follow, drop a subscription, and drop comments if you have any questions. I'll catch you on the next one. And everybody else, you're free to leave or you can stay and ask more questions. But peace out, everyone.